Hello everyone. Welcome to listen my speech about an optimized decentralized power sharing strategy for wind farm deloading. I'm Xinkai Fan from Xi'an Jiaotong University. As we all know, the wind power generation capacities are increased worldwide in recent years. Sometimes the wind farms are not allowed to give its maximum power generation into the power grid. This may be due to the following reasons. For example, the transmission capacity limitation, the load limitation, to ensure transient stability, or some other reasons. Typically, large-scale wind farms consist tens to hundreds of wind turbines. So there is a problem that if a wind farm needs to deload, how should the operator share the power reference to each wind turbine? In this paper, we try to solve this problem. The power sharing problems can be formulated as following equations. Here, we considered three goals in the optimal problems. The first one is give priority to the newer wind turbines. This part tries to make the newer wind turbine to produce more power and undertake more dynamic stress. The second one is trying to minimize the dynamic stress of the wind turbines, which include two kinds of stress. The first one is the cycled thrust passed from the blind to the tower, and the second one is the torque on the gearbox or the shaft. The third goal is to avoid overspeed problem during the transit, which may lead to unexpected protection tripping. To implement the optimal control, we utilized a decentralized control strategy called unsynchronized AIMD. This control includes two core stages. The first one is called additive increase, which means each wind turbine linearly increases its power generation if the total output of the wind farm is higher than the power system's operator's demand. The second stage is called multiplicative decrease, which means if the total output of the wind farm is higher than the demand, then the control center broadcasts an empty flag to ask wind turbine to reduce their power generation. After the wind turbine gets the empty signal, only a subset of the wind turbine decreases its output power. In particular, each wind turbine performs the multiplicative decrease according to a locally computed probability. This range can be expressed by the following algorithm. We tested our strategy in a wind farm consists 10 wind turbines. The result shows that the total power generated by the wind farm is closely follow the desired reference signal. And the proposed decentralized AIMD strategy is closely similar to the centralized implication. At the same time, the control can effectively achieve the three goals mentioned above. The following result shows the most relevant features of the proposed decentralized algorithm. To be specific, this strategy is inherently robust against possible failures, like communication failures or some unexpected wind turbine tripping. When compared with the centralized control methods or the existing distributed strategy, the result shows that our proposed decentralized method greatly reduced the need for communication. To draw a conclusion, a deloading operations of the wind turbines in a wind farm was proposed and validated in this paper. In particular, the power was shared according to the utility functions that take into account both the dynamic and the static stress of the wind turbine. The AIMD is very attractive and efficient for practical application as optimal power sharing. This method does not require massive communication and very robust to unexpected failure. Thanks for your listening. That's all of my presentation.